Hello students, in this video we'll discuss the DeMorgan laws for taking complements of unions and intersections. If we're given two subsets, A and B, of X, some larger set, then we have the following two rules, the DeMorgan laws. The first law says that if I look at A union B and take the complement of that, that is the same as A complement intersect B complement. The second is that if I look at A intersection B complement, that's the same as A complement union B complement. And so what we can do is we can visualize this geometrically for one. So if I have a set X and then I have a set A, let's say that A looks like this. So A is over here, A is this entire part of this rectangle. And let's say that B is this rectangle over here. So B will be this part over here. And so this sliver over here, this little sliver over here, is A intersect B. And so now we ask the question, well, what would A complement intersect B complement look like? Well, A complement in this drawing would be this part over here. And B complement in the same drawing, if B is over here, then it would be right over here. In this case, we see that A complement intersect B complement is empty. There's nothing there. So here, in this example, A complement intersect B complement is empty. So we can prove these things mathematically as well. If we were to prove one, for example, so let's do the proof of one. The proof of one, we suppose that there is a element X, which is an A or B complement. Now we unwind what that means. This means then X is not in A or B. And if X is not in A or B, then X is not in A and X is not in B. So X is in A complement, that's what that statement means, and X is in B complement. So what we have over here is we have A union B complement is contained in A complement intersect B complement. Let's do the opposite direction. If we suppose that there's a point Y, which is an A complement intersect B complement, then Y is not in A, and Y is not in B. Because Y is in A complement, so Y is not in A, and Y is in B complement, so Y is not in B. So what we have here is we have Y is not in A or B, since we're not in A and we're not in B. So we're not in either A or B, and hence Y is in A union B complement. So we've shown that A complement intersect B complement is contained in A union B complement. So altogether we've shown that one is a subset of the other, and the other is a subset of the first, and therefore we have equality in this. One thing we should remark is that it's possible to extend this to more general indices of unions. So if we recall two things, we have, of course, the union from 1 to infinity of AI is simply just the set of all x in your space x, or set x, such that x is in AI for some index I between 1 and infinity. Similarly, if I do the intersection, I goes from 1 to infinity of AI. This is the set of all points x, such that in x, such that x is in AI for all I. And so what did the DeMorgan Laws say for this? Well, the DeMorgan Law says, if I look at the union from I goes from 1 to infinity of AI, and then take the complement of this whole infinite union, this will be equal to the intersection from I goes from 1 to infinity of AI complement. And analogously, so that would be the analog of number 1. This would be the analog of number 1. And the analog of number 2 would be if I look at the intersection, I goes from 1 to infinity of AI, and then complement it, this will be the union, I goes from 1 to infinity of AI complement. And I've stated these DeMorgan laws for countable unions, but it's also true for any union over any indexing set. So the general rule is that if I do the complement of a union, that's the intersection of the complements, and then if I look at the complement of the intersection, that is the union of the complements. And so that general DeMorgan rule will work in general. And so it's oftentimes better to just think it through linguistically as opposed to trying to draw a complicated diagram to prove something that's very elementary from a linguistic standpoint. Thank you very much.